Hi everyone, we'll get started in just a few seconds. I'm going to wait for a few more people to connect, and then we're going to get started. So in the meantime, I would like some feedback. If you can see me, if the audio is working, if you can see my screen right now, please let me know. Microphone and screen are working. Thank you. Okay, so we're going to get started right now. Everyone, welcome. In today's webinar, we will be discussing the basics about neural networks. So we'll be talking a little bit about their inner mechanisms, how they work, that sort of stuff. We'll also be discussing where we can apply neural networks, how we can use them, not just for fun purposes, but in the real job market, in the real economy, and that sort of stuff. So this webinar is going to be about 2 hours long. We are going to, for the first 5 minutes, we will just be talking about our organization. So I will introduce you to our organization, and then we'll get onto the content for the rest of the webinar. And if you have any questions at any time, please feel free to ask at any time. Just type in your questions in the chat. I will periodically be stopping to read out some questions and to answer them. So one more thing, we've had some issues with the internet. I don't think we'll have any anymore, but just in case, like there is maybe a 1 in 10 chance that at some point I might disconnect. If that happens, then please stand by for like a few minutes while I reconnect. So that's probably not going to happen, but just to be extra sure. And I will just drop the contacts of our university in the chat right away, and I will be referring to that later. So let's talk a little bit about our organization. We are a commercial university. We teach people how to make neural networks. We have a collection of courses just for that purpose. So we are almost 2 years old, and we have had almost 2,000 people enroll in our courses so far. It says that we have 15 courses here. We have 2 main courses. So in our main courses, our 2 main courses, they're basically variations of the same course. One of the courses is geared more towards people who have never programmed in their lives before, who don't really know what a neural network, what artificial intelligence is. Plenty of the people, the majority of the people who come to us are like that. So people come to us from all kinds of walks of life. So just fresh out of high school, fresh out of college, university, maybe from some other careers like doctors or businessmen or bankers, like the jobs that don't really have anything directly to do with artificial intelligence. And in our main courses, we basically start from the basics, and we cover the majority of the topics that we have about neural networks out there today. I'm not going to say every topic because artificial intelligence is a huge science. It's a huge field, and for the most part, it is very new. It is developing very rapidly, but we do cover a lot of topics. Like we start with the basics, and then we go over onto autoencoders, variational autoencoders, generative algorithms, deep neural networks, and so on. So we have all of the content in all of our lectures is made by us. It is owned by us. It is made by our developers. Right now, we have 318 pieces of content. So that's 318 unique lessons, lectures in all sorts of different courses. And we are constantly making more and more. We recommend that you take about a week to study 1 piece of content. So if you were to do that for all 318 different lectures, that would take you over 5 years. And by then we would have made even more courses. We are constantly just making new, more and more material. We have a whole team of AI developers that does just that. And the other thing we do is we take on commercial projects. So we have customers that ask us to make some commercial neural network, some artificial intelligence for some commercial purpose for them. And we have had hundreds of customers like that. We have been approached by huge companies, by entire governments. So we have a few that really stand out. The first one is where we made a neural network that allows a drone to be piloted automatically. So much like Tesla's autopilot, but it's a little drone, just a little drone that sort of zips around some building, some construction zone, and it doesn't just fly around aimlessly, it actually does something. So it takes a bunch of pictures and then it does what is called image segmentation on all of those pictures. So it might see, for example, it might see a wall and it might see that that wall is painted or it's not painted. And it might say that that wall needs to be painted. Furniture needs to be installed over there. If the door is open, it might choose to fly through that door. Or if there is no door installed in the doorway, it might store the data that a door still needs to be installed. So by flying day in and day out over many days, it can provide feedback of how much work is being done, how much work still needs to be done, and so on. And we've also made a few medical neural networks, a few AI projects that are related to medicine. So one of them involves skin diseases, so like skin rashes, stuff like that, where you could take a picture and based off that picture, an AI would just analyze it and it would give some kind of a diagnosis as to what the disease is, how it's to be treated, and so on. So right now, the neural network, that AI isn't perfect. It's not the most accurate, but we are working on improving that accuracy. We think that it will become a lot more accurate once we increase the data set. So it doesn't fully replace doctors, but it can give some sort of preliminary diagnosis. And another neural network that we have that performs a very similar function. So instead of, the only difference is that instead of just taking an image, it would take in either some textual description or some audio description of all of the symptoms. So if, for example, you could say something like, oh, my back hurts, my chest hurts, I have chest pains when I do this and that. And provided that it's a concise diagnosis, that neural network is accurate to within about, I believe it's like 98% of cases. So that is a higher accuracy than what most doctors can offer. And we will be observing this tendency in neural networks a lot. A lot of neural networks, which are well designed, which are trained on a large data set, can actually give better results than human experts who have spent their entire lives studying that specific field can. So once again, this doesn't fully replace doctors, but it can give some sort of preliminary diagnosis and it can lighten the workload of actual doctors by quite a bit. And we have another project that I just really want to touch upon very quickly. We are working upon a neural-computer interface. So a neural-computer interface is like, you know how we control our computers? Well, usually we do it with a mouse and keyboard. With cell phones, we touch the screen, we tap the screen from time to time. We are working on something that does something like that, but using the power of one's brain, like literally using one's brain waves, where some electrodes would be attached to the person's forehead, and those electrodes would read their thought waves, they would record their thought waves, and based on those thought waves, you could actually control a computer. You could type in text. We have managed to do that, by the way, right now. We have managed to get people to type in whatever they want to appear on the computer, like some letters, some text, just by using their brain, just by thinking really hard that they want that specific text to appear onto the screen. But we want to expand that. So right now that's mainly being used for people with disabilities. We want to expand that to just let us control the computer in general, like move the mouse around, maybe even like close tabs, close windows, maybe even do something within some document or something like that. So that is really exciting. And one more thing I want to mention, just very quickly before we head on to the content, is that our organization exclusively specializes in artificial intelligence. Everything that we do is in some way, shape, or form related to AI. So we have some questions. Similar to Neuralink. Yeah, kind of like that. Will there be a replay? Yes, it's being recorded and there will be a YouTube link at the end of that. I believe they'll contact you and give you the YouTube link at the end of that. The people in our department. Here we have one more question. Great. Okay. So once again, if at any point in time you have any questions regarding any of the material that we're going to cover today, I would be more than happy to discuss that. I would be more than happy to answer any questions. So to start off today's webinar, let's talk about what neural networks are, what artificial intelligence actually is. Let's start with the terminology. So artificial intelligence is anything that performs some kind of intellectual task. An intellectual task is anything that cannot be solved using deterministic logic. So for problems that involve using deterministic logic, we have tons of problems like that. Personally, I play a lot of video games, so I'm going to use that example. We have a lot of video games on the market today. And it doesn't have to be video games, it can be really any document. I just think video games are a better example. When you're playing some video game, the game is actually just a collection of code. So just a bunch of instructions issued to the computer that is running on an infinite loop. And that loop ends whenever you hit the quit game button. So all of the logic that is in the game is performed deterministically. Even the enemies, the quote unquote AI isn't really AI, it's just some enemies that are being controlled by deterministic logic. When the computer sees that, for example, if you're playing Pac-Man, if it sees that like the ghost or whatever is hunting you is right here and you are right here, it might tell the ghost to move in this specific fashion or to find a path that is going to lead to the player so the ghost can then eat the player. And every single function is performed in that same way. If you think about it, there is a crazy amount of things that's happening there. So whenever some audio plays, a lot of modern video games will have some functionality that reduces the volume based on how far the noise occurred from the virtual position or which virtual direction the noise occurred from. So for example, if the noise in your virtual world, in your computer world, if some bushes or something are rustling to your right, you will hear that audio play in your right headphone. And if that happens from the left, you will hear that audio play in your left headphone, and so on. And every single function is controlled in this manner. When it comes to 3D graphics, which is what we mostly have nowadays, there is just another world of complexity there. I'm not even going to be going over how 3D graphics work, because if we were to do that, we would be stuck here for days. But needless to say, it is nothing short of incredible that we can generate the illusion of 3 dimensions by plastering a 2-dimensional image onto our screen in a specific way, and then that if the object moves in some way, that image changes, or if the camera moves, that image also changes in this very specific way that maintains the illusion of 3 dimensions. That is nothing short of incredible. In fact, just in general, whenever we're playing any video games or even just using a basic Microsoft Word document, the amount of code that is involved in that, the amount of instructions the computer is executing per second is absolutely incredible. And it's really a feat that we as a species have managed to achieve something like that. But no matter how complicated that code is, every single step in it is predetermined. So every single instruction was issued to the computer by some programmer at some point in time. The computer doesn't actually do any of its own creative thinking. We can solve a lot of problems using this deterministic logic, but there are some problems that we just cannot solve using any deterministic logic. So one of the simpler examples of this is classifying between cats and dogs. Let's just pretend for a second, hypothetically, that we want to distinguish different pictures of different cats and dogs. Like we have one image here that contains a cat. I'm not going to draw a cat because I'm a horrible artist. And then we have another image here. Let's just say that this is where we have a cat and this is where we have a dog. And somehow the computer has to distinguish between which picture contains a cat and which picture contains a dog. It has to know what a dog is and it has to know what a cat is. So in theory, it would be looking at the image pixel by pixel. If we have this combination of pixels, it might be a dog. If we have some other combination of pixels, it might be a cat. But there are millions of pixels and the number of possible combinations there is just, it's absurd. It is way too big to be expressed in anything but scientific notation. So, and there are different ways that you can draw cats and dogs as well. They can be like realistic photographs. They can be photographs with some filter on them. They can be something like an Microsoft Paint doodle or a pencil drawing. The cats and dogs have to be of different breeds. The cats and dogs, they might be in different poses. So for example, there might be one photograph of a cat mid-leap, or there might be another photo of a dog just lying around sleeping. And for all of these pictures, there has to be some general algorithm that is going to tell us which picture is a cat and which picture is a dog. This is a very simple task to solve from the perspective of machine learning. This is kind of like the hello world of machine learning almost. Or for example, if we want to categorize different hand-drawn digits, we could have a number 1 that's drawn like this, or one that's drawn like this. We can have a 2 that's drawn like this, or it can be drawn like this. And we have to know which digit is which. Which digit is a number 1, which digit is a number 2. Once again, it is almost impossible to solve using any deterministic method. In theory, it would be possible, I think, but in practice, it would be, like, in theory, it would be possible to solve only if you have a supercomputer that uses all of the computational resources of the universe or something like that. In 1,000 years, I don't think anyone would create an algorithm like that that can give us any reasonable accuracy. But from the perspective of machine learning, this is a very easy task to solve. And there are many more practical examples of this. So for example, if we want to predict the weather to a higher accuracy than any deterministic method can give us, if we want to convert audio into text, so for example, maybe we might have a machine learning algorithm that converts everything that I'm saying right now into text so that it can be read later. Or converting text into audio. You could probably convert text into audio deterministically, like reading out each word individually, like AI performs intellectual tasks, something like that. But if you want to add some sort of sentence flow, like if you want to read AI performs intellectual tasks, that's going to be much more complicated. And there are many other more topics like that. Your thoughts on correlation and AI. Can you be a bit more specific, please? What exactly do you mean by correlation? So on our next slide, we have even more examples of where AI is used. So some practical applications, or well, not all of these are practical applications actually. Some of these are just fun applications. For example, right over here, all of these faces were actually generated by a computer. None of these pictures are of real people. And if you look closely, you can see that column by column, they are actually the same person, kind of. Like you can see that they have the same pose, that they're looking at the camera from the same angle, and so on. We can edit photographs in this exact same manner. So that's what we have in the next example. So in the top row, we have the original image. In this middle row, we had like some scientists, some people who created this neural network. They erased a part of the original image and then they drew in some features. Like they drew in, for example, this weird, goofy looking hair here. And then in the bottom row, we get the neural network actually editing the entire photo to make it look like it wasn't just copy pasted using Photoshop, but to make it look like all of these features were actually there when the picture was taken. So right here, we have a lot of examples of neural networks that are related to images. So for example, here we have, this is my personal favorite, by the way. This is an example from NVIDIA where in the left, we have the image that was drawn sort of like an MS Paint doodle, like they specified. They have the colors down here where the computer knows which color corresponds to what. And then the computer generates a whole realistic looking landscape based off of that, which is really awesome. And unfortunately, you don't get to see this here, but in one of our bonus courses, we go over this whole neural network and we can see its demonstration live. In fact, you can actually look it up live on YouTube. When they, for example, draw this waterfall here, the waterfall, it doesn't just appear. It doesn't just edit the photo where the waterfall actually is, it edits everything around it. So the rocks, for example, become different. Since whenever we have waterfalls, we have some erosion going on, we can see that happening. We can see the erosion being added in, like live. We can see reflections in the water. We can see the water reflect some of the things that we have in the actual landscape. And the amazing thing is that none of these correlations were actually explicitly taught to the neural network. So we will be going over why this is, but we won't be telling the neural networks any of the correlations ourselves. The neural network is just going to look at a bunch of data and it's going to find all possible correlations on its own. And then we have image segmentation. So this is like a higher level of the example of what we had with cats and dogs. So for example, the neural network knows that this part of the picture, like this little corner, contains a car. And this little corner contains, like maybe the top left corner contains a person, and it highlights that whole person, or it highlights that whole object of interest in some color, and it classifies what that object is. So something like that would be used, for example, in Tesla's self-driving cars, which is what we have here. We have some more examples. So this example where in the left, once again, we have an original image, and on the right, we have that whole image redrawn to make it look like it was filmed in the summer. Like the left side just contains some dash cam footage, and the right side contains that same image, but it looks like it's in the summer. So the sky is of a different color, trees have leaves, any snow on the ground gets replaced with grass, and so on. This is another really nice example from NVIDIA. And this is an example of photographs taken in 360 degrees being converted into 3D models. So this is not something that humans can do very easily. So we can apply neural networks even to areas where humans just physically can't work. They can't solve these problems. All of these examples are related to image data, but neural networks are by no means limited to images. They can work in pretty much every sector of the economy, in pretty much every industry. I want to say every job, but they might not work in some very niche jobs, but for the most part, they can be applied to a huge number of different fields, a huge number of different cases. So we don't have anything general right now. One thing I also want to mention, we don't have anything that's like in the movies where we have general artificial intelligence, where we have like Skynet, or where we have maybe even something a bit goofier, like from the Star Wars movies, we have droids that are sentient. We don't have artificial intelligence like that yet. Instead, each of these separate functions are performed by something that is called narrow AI. Narrow AI is very good at performing one specific subset of tasks, but only that one specific subset of tasks. So it has some flexibility. It's not a deterministic algorithm, but for example, an algorithm that can drive your car, that can drive a Tesla, like Tesla's autopilot, it might be able to do that much better than most humans can, maybe even better than any human can, but it won't be able to predict the weather. We need a different artificial intelligence to predict the weather. And about some other areas where this can be applied. So there is a very humorous example on the internet of a Harry Potter book being written by an artificial intelligence, and people actually made an animation out of it. It's not a very good book. Let's just leave it at that. Neural networks, they can't mimic humans in a lot of ways yet. Like they cannot mimic a lengthy human conversation, for instance. So the book, it wasn't, I'm not going to say that it was bad, but it was very humorous. Like you can find a YouTube video of it. You can find it, everything that's happening actually being animated. It is really hilarious. It's called Harry Potter and the Portrait of Something That Looked Like a Pile of Ash. And I had to watch that again for all of the laughs. So with that, let's talk about data science. Wherever we have neural networks, we have huge collections of data, and we will be analyzing that data to extract any useful information. This is where data science comes into play. Data science is one of, it's one of the very most in-demand professions out there right now. Like good data scientists are immensely in demand, and it's going to stay that way for, most people believe, about 30 years. After 30 years, we might have something else. Like maybe some people are saying that after, like in the distant future, we will have all sorts of biologists, like people who can do genetic engineering, that sort of field will be very in demand, that genetic engineering will replace data science. But for now, data science is just, it's king. Data science is the very, very most in-demand thing out there. So data science is not a new thing. Whenever we think of data science, we usually think of some people in some big company meeting together. Maybe they would be looking at a pie chart, something like this. Please excuse this horrible imitation of a circle. Let's pretend that this is a circle. They might say that maybe this percentage of their customer base belongs to some demographic or something like that. They might have a line chart that outlines how much money some company made, something like that. So these are examples of data science, extracting useful features from a huge collection of data. And wherever we have neural networks, we will be doing that. So the type of data science that I just described has been around for centuries. Historically speaking, like let's say 50 years ago, if someone were to apply to a mortgage, like to get a mortgage, they would want to get a bank loan, something like that. The bank would actually hire a data scientist to help them know who is creditworthy and who isn't creditworthy. So if you think about it, banks are normally interested in giving people loans, right? Because the bank knows that they will be paid that loan back plus some percentage on top. But sometimes there are people who, for whatever reason, can't pay back their loans. They end up defaulting on their loans. And the bank isn't interested in giving these people their loans. So this is just one example. We also have similar examples whenever it comes to insurance companies. All of these companies, they would hire a data scientist who would look at the data of all of their customers. So the bank would ask all of their applicants for their personal information, like how much money they make, how long they've been employed, where they work, stuff like that. They might even ask, and I don't know if they ask this, by the way, I've never actually applied for a bank loan, but they might ask for something like if they're married, yes or no. They would probably ask the person's age, how many kids they have. Maybe they might ask like how many kids they have and stuff like that. And the data scientist's job would be to create some mathematical function. So like f of x, y, and z with just a bunch of different variables, like some mathematical function that would read all of this data, that would take in all of this data, and it would produce some output, like either a 0 or a 1, where 0 would mean that the person is not creditworthy, and 1 means that that client is creditworthy. So this function, it would be up to the data scientist to make some sort of function that broadly fits all cases or the vast majority of cases that, given their credit history and a bunch of other parameters, can classify whether or not the bank wants to give the loan to that person. But as time went on and on, we've discovered that this whole process can actually also be done by machines. So that is where machine learning comes into play. We have two types of data science. Analytics, that's basically what I just described. That's where some human data scientist would look at a collection of data. They would try to design a mathematical function that would try to give some output, and that output is going to correspond to whether or not the bank believes that person to be creditworthy. Some data that isn't numerical, like married, yes or no. Married is a yes or no answer. So that might be converted to numerical format. Like no would be converted to 0, and yes would be converted to a 1 or something like that. So historically, this whole procedure was done by machine learning algorithms. But nowadays, sorry, what am I saying? Historically, this whole procedure was done by humans. But now we are seeing more and more of this work being done by various machine learning algorithms. So we have noticed that computers can do this same procedure. Their logic is, generally speaking, a little bit more abstract. It's not the same as a human's logic. They can't explain why the function that they created is the way it is. So for example, a human might be able to explain, they might be able to give some intuitive explanation as to why the whatever function is, whatever the function that they made, why it is the way it is, but a computer isn't going to do that. So as time went on, as computers became more and more powerful, we have seen more and more of this process being taken over by machine learning algorithms. For example, if we were to look back into the year 1995 or something like that, the approximate graph, the approximate representation of how much is done by computers and how much is done by humans would look maybe something like this. Already back in 1995, a lot of this work was being done by computers. Humans still did a lot of work, but not everything. So we had a bunch of classical machine learning algorithms. These are like k-nearest neighbors, support vector machines, something like random forests. There are dozens and dozens of such algorithms that can perform a very similar function to what the hypothetical data scientist that we talked about did. And then we also have one type of machine learning algorithm that is called a neural network. Neural networks date way back to the 1950s. They are not new. But historically speaking, they were not very powerful. Historically speaking, classical machine learning algorithms like support vector machines and k-nearest neighbors dominated. But as time went on, as we've developed more and more powerful computers, as we've developed more and more powerful CPUs, we have been able to make neural networks that are larger, that are more complex, and they have been able to give us even better results. So if this is what this whole graph looked like in maybe something like 1995, then nowadays it looks something like this, where neural networks just dominate the field. Neural networks are almost exclusively used for machine learning. So this graph doesn't even do it justice. Right now, we maybe would have this, we still have some human data scientists. Actually, we have quite a few human data scientists that just do all of this work manually. But a huge portion is being performed by neural networks. Like 95% of this work is being performed by neural networks. Only in the case of some relatively simple examples are classical machine learning algorithms better. So only the very The only areas where classical machine learning algorithms really outperform neural networks are ones where the task is relatively simple, and if we assign some huge neural network to do it, the neural network will basically start overthinking the problem, and we don't need a lot of I'm going to say like intelligence to solve some specific task if it's like a very simple task. So the portion that is being done by neural networks is still expanding. And within these machine learning tasks, we have even more divisions. We have simple tasks. So simple tasks are like classifying cats and dogs, classifying between different digits, something that doesn't require too much thinking, just looking at two different pictures and deciding which one is a cat or a dog. That's an example of a simple task. Something like predicting the stock price tomorrow or 5 days from now, that might be a simple task in some contexts. But we also have a very important field that is called deep learning. These are tasks that can only be performed by machine learning algorithms. So deep learning is like when Tesla drives your car, where Tesla's autopilot drives your car around. Something like converting audio into text or segmenting an image. These are much more complicated tasks that really can't be done by any of the classical machine learning algorithms. And they are exclusively performed by deep learning algorithms. So we have a few more questions. Please send the link when it's done. The link will be sent by our marketing department. That's not something I do, but the other people that are working with us will absolutely send you that link. So far, we've talked about how neural networks are so amazing. So let's talk a little bit more about their advantages, and we'll also touch upon just a little bit upon some of their disadvantages. So the first big advantage is that neural networks learn on their own. We don't need to explicitly tell them any of these correlations. So any of the correlations that we have in any problem. So for example, if we're trying to classify different trees, if we're trying to see which trees are oak trees and which trees are birch trees or something like that, just for example's sake, the neural network doesn't need to be told explicitly that wherever you have green needles, that's a pine tree, something like that. The neural network is going to learn all of that on its own, given a huge collection of data. It is going to process all of that data on its own. And that's where one of the disadvantages come into play. Neural networks require a database to learn. They aren't able to learn by themselves. Well, they are able to learn by themselves, but they need information to learn from. And that information is going to be given to the neural network in the form of a database. So some collection of data. If we wanted to classify images, we would give it a collection of images. We would show it a collection of images, and we might tell it that these images are cats and the animals portrayed in these images are dogs. These databases can be quite difficult to obtain. So oftentimes people need to go out there manually and actually physically collect that data by themselves. That is not an easy task. So this is a huge downside. To give an analogy, when a neural network is created, so to speak, it doesn't actually know anything. It learns by example, and we need to show it these examples. If we were to hypothetically have a human baby that was just born 2 minutes ago, let's pretend once again, for example's sake, that we can communicate with this baby. We can tell it things like we can talk to it. Or maybe it isn't like a human child. Maybe in some distant future, we have adult humans who live in space on some sort of colony on Mars or something, and they never saw trees on Earth before. they wouldn't know what an oak tree versus a birch tree is, or what a cat versus a dog is. If those animals, if those plants no longer exist, they have no way of knowing, right? They would never have seen either animal or either plant in their entire lives. So if we want to teach some sort of future Martian, some sort of future human on Mars as to what a cat is and what a dog is, you can think of us as showing them a few pictures and saying, okay, these are cats and these are dogs. This is what cats look like and this is what dogs look like. We basically do the exact same thing with a neural network. Except a neural network takes much more than just 5 or 10 or however many examples that you think a human that would suffice for a hypothetical human. They would need thousands, tens of thousands, hundreds of thousands of examples. The more the better, really, but 5 or 10 isn't any good. We would need a few thousand at the very, very minimum. So someone has to go out there and actually find and collect all of this data. The second advantage is that whenever we create neural networks, the people who create those neural networks, they don't have to be renowned experts in whatever field that they're creating a neural network for. So for example, AI developers in our university are creating neural networks for medical purposes right now, but at the same time, they don't need to hold medical degrees to do that. The neural network extracts any correlations by itself. So for example, if we want to make a neural network that given some MRI scan or something like that, it can classify whether or not a patient has pneumonia, or given some other scans, whether or not a patient has cancer, whoever is designing that neural network doesn't need to be a doctor. It would help to be a doctor, since if you're a doctor, you would know which features you might need to pay attention to a little bit more, what your data set might look like, what you would want your data set to contain, what sort of information, and so on. But typically, in the worst cases, we can just consult actual experts about this. So we might ask actual doctors about what we're looking for. Or if the data can only be collected in space or something like that. Or if it's some strange scientific related data, like corresponding to some very narrow scientific field, we can consult actual experts in that field. We can ask them to give us whatever data they have that is stored somewhere. We can ask them what we're looking for to classify something. And then we would make a neural network that can learn all of these correlations on its own. And the last advantage, well, it's not really the last advantage, more like the last advantage that we are going to talk about right now. If we were to talk about all of the advantages, we would be stuck here for a very long time. Neural networks, a well-made neural network that is trained on a comprehensive data set that has an architecture that is sufficiently good, is going to give us better results oftentimes than human experts can, who have trained their entire lives studying that specific field. So oftentimes, for example, for Tesla's autopilot, the no-brainer things are that it can, for example, it has faster reaction times than most humans do out there, probably faster reaction times than any humans. It is able to pay attention 24/7. But oftentimes it might also be able to extract more specific information. So it might be able to see things on the road that human drivers really can't make out at all. Or in an example that is more closely related to our university. At the end of our main course, we have our students complete thesis projects, which is basically any big project that they want to create, just a neural network that is going to be created for whichever purpose that they want to create. There is a lot of sort of creativity involved in that. We had one student that made a neural network that analyzed some metals to see if there are any deficiencies in those metals. So for example, it would, I don't know what data it exactly read, but I imagine it might read like some audio data, like sonar, or it might look at that picture of that metal very closely. It might see if there are any microfractures, something like that. And based on all of that data, the neural network was able to tell whether or not there were any defects with 98% accuracy, whereas human experts were only correct about 85% of the time. Human experts who have spent their entire lives studying that specific field. So neural networks can still sometimes be prone to error, but oftentimes they are less prone to error than humans are. Now on to the disadvantages. Neural networks require lots of processing power. This is what prevented us from harvesting the full potential of neural networks for many, many decades. This is why neural networks have only really become popular within the last decade or so. And even nowadays, the amount of processing power we have is still a big bottleneck. I mean, if you think about it, it's actually, technically, it's the only bottleneck that exists. So it's the only limitation that we have. Basically, the more processing power we have, the happier we are. But nowadays, using a CPU still won't give us any good results. CPUs to this day simply aren't powerful enough. We would need to use GPUs, graphical processing units, just to perform all of the operations that we need on neural networks, just to train our neural networks. So GPUs, as it turns out, they are well suited for all sorts of matrix-related operations, like adding matrices, multiplying matrices, that sort of stuff. And as it turns out, the process of training and using neural networks is basically that, doing matrix operations. And GPUs, in my experience, they are about 50 to 100 times faster than CPUs that were made around the same time. So we need GPUs to train neural networks. Otherwise, it would take forever. A neural network that we would normally train in 12 hours would take 2 months to train. That is obviously unacceptable. But for the sake of our courses, so in our courses, we're going to be using GPUs on the cloud. Google Colaboratory, Google services offer free GPUs that we can use for some amount of time. So if you don't have a GPU that you can use, you don't have to worry about that. And the final disadvantage that we have is that neural networks are what is called a black box. Whenever we train neural networks, they basically perform the exact same procedure as the human data scientist did back in our example with mortgages. So the neural network looks at all of the data and it tries to make some very complicated function that, given some inputs, it gives the correct output. In our example, whether or not the person is creditworthy. In some other example, it might be whether or not the picture contains a cat or a dog, or what the stock market is going to be like 5 days from now. All of these sorts of examples, it's going to provide an output. It's going to design some huge, very long mathematical equation that is going to process all of that data and give a single output. The neural network is effectively going to create that equation by itself. But it's not going to tell us why every part of the equation is the way it is. The questions that the neural network will effectively be asking are going to be very strange, and they're going to be very removed from human logic. But for some reason or another, we will be able to see that whatever the neural network does, it works. It just works. We won't know why it works, but we will see that it works. So neural networks cannot explain why they use the logic that they use. And this is a problem for some fields where it is required to explain step by step as to how the conclusion was reached. So for example, we have court cases, something like a court case where we have a defendant and the accuser. we could probably create a neural network that would just look at the faces of the defendant and the accuser, and just by analyzing their faces, it might determine the guilty party. Or it might do something a little bit more clever. It might look at some more data, like someone's heartbeat, someone's blood pressure when they're talking, basically like a lie detector analyzing if they're lying or not. There is actually a field in science, by the way, called socionics, where you can, to some degree of accuracy, determine the characteristics of a person, like their personality, just by looking at their external features, like their face. It's nowhere near 100% perfect, but even if we were to pretend that it's 100% perfect in our hypothetical world, something like that would never be accepted. We would never have a neural network that would just take a picture of the defendant and the accuser and then just say, the defendant is guilty, 50 years in prison, death sentence, worst punishment imaginable. That is never going to happen because the neural network cannot explain why the person is guilty. We might see that it predicted the guilty party correctly 99.99% of the time previously, but in any case where we need to explain specifically how a conclusion was reached, no one, barring some, I don't know, like some crazy kangaroo court, no one is going to accept an argument like that. And another field where we can't really apply neural networks to their full potential because of this is science, all sort of scientific related work. So we have judicial stuff and scientific work. So whenever scientists design some equation or derive some equation, for example, when Einstein derived the famous equation E equals mc squared, Einstein actually gave not just one, I believe Einstein gave something like 3 or 4 different arguments as to how this equation could be derived. Also, fun fact, someone else derived a very similar equation, something close to E equals mc squared, shortly before Einstein. I think they actually derived E equals mc squared, but they just didn't realize the meaning. They derived it from sheer math, although don't quote me on that though. So these scientists, they explained the intuition behind this equation, or they at least explained every step in derivation. They explained the logic of how any equations like these were derived. However, a neural network, even if it can design some equation, which it can in some circumstances, once again, it isn't able to tell us why that equation is the way it is. And because of that, no scientific community would ever accept an answer like a magical neural network created this equation, please accept it, guys. No one is ever going to take that seriously. So if anyone has any questions so far, I encourage you to ask them. I would be more than happy to answer them. For now, let's talk a little bit about what the developer's work consists of when we create neural networks. So far, we've talked about how neural networks, they're so amazing, they can learn on their own. However, if that was the case, if neural networks performed every single little function on their own, we would be out of work. We would not have any work. So what do the actual developers do when they create neural networks? The very first step, whenever you create a neural network, whenever anyone creates a neural network, the neural network has to have some data to train on. So once again, going back to the example where we made a hypothetical example of a baby that was just being born. Imagine some old man walking up to that baby and asking, okay, Billy, see those 2 trees in the distance? Can you tell me which one is an oak tree and which one is a pine tree? The child would just look at the person, the old man, as if they're crazy. Like, I was just born. How do you expect me to know what the hell a tree even is? The neural network works in much the same way. it needs actual data to learn from. And that data needs to be obtained from somewhere. So it's often said that collecting a data set is actually like 60, 70% of the entire work in the entire project of creating a neural network. So this is a really lengthy process. Huge companies who have access to large amounts of resources might hire entire departments just for this purpose. They might use like a department of 20 people plus 50 or 100 freelancers just to collect one data set for some neural network. Freelancer developers, so people who make less fancy neural networks who don't have access to as many resources, they might still be hiring one or two freelancers just to obtain that data from somewhere. Sometimes we can work with open source data. Sometimes we might look up some data online, just write some code to parse some website and generate a data set just like that. Sometimes we might have a data set that is just already ready for us. Maybe there is some data from some other project, like leftovers from some previous projects. But a lot of the time, people actually need to hire other people to go out there and physically collect all of this data. This process is usually done by other people. So it isn't done by the people who are actually trained the neural network. This is usually done by a whole other department, or developers might hire freelancers or something like that. After the initial data set, after even like a tenth of the overall data set has been collected, the actual developer, so like us, can start trying out some architectures. So neural networks consist of neurons. And these neurons might be connected to some other neurons in some elaborate fashion. These neurons might do different things. All of that is part of the architecture. So the data scientist, the AI developer, would create some architecture through which the neural network is going to function, which the neural network is going to use. And they might see that some architecture doesn't do so well. They might try out multiple architectures until they find one that gives fairly good results. And that's when they would be observing the accuracy that they would basically be observing how well each architecture performs. They would be looking at every neural network that they've made. They might see that this first prototype neural network didn't do so well, so maybe we need to tweak some things, tweak some layers, add some neurons in these places, and then it starts performing better. And for every neural network, they would try to observe the accuracy to get the highest accuracy in the end. Then they would conduct a series of tests. So we have two parameters that we are going to be talking about in much greater detail very soon. We have the accuracy from what is called the training set. This is how well the neural network performs on data that it's already seen before versus data that it's never seen before. So for example, we might have two different pine trees. We might have two pictures of two different pine trees. The first picture is used to train the neural network, like to tell the neural network, okay, neural network, this is what a pine tree looks like. And the second image will be shown to the neural network without telling the neural network what the answer is, what kind of tree it is. And it's going to be used to see if the neural network has actually learned and if it can predict correctly that this image represents a pine tree. Very often, neural networks do something that is called overfitting. So a neural network might overfit. That's when it basically remembers all of the data that it's seen during the training process, but it hasn't learned to generalize the data. So that's like a student studying for a math exam, for example, and in the practice questions, like we have practice questions before the final exam, right? So they might see something like 7 times 5 equals 35. But then the final exam might have a question like 7 times 6, and they wouldn't know the answer. They haven't actually learned how to perform this operation. They've just memorized all of the questions that they've seen. They've memorized the answers to all of the questions that they've seen. We don't want that to happen. So this step is basically making sure that that doesn't happen. There are many ways, many methods that can be used to prevent overfitting that we go over in our main course. But the aim is to ensure that overfitting does not happen. And at the end of that whole process, we get our final product. That's just going to be a small file that's stored somewhere on our hard drive or somewhere in the cloud that contains the whole equation that the neural network has generated. And we would want to actually use that somewhere. So for example, we might have neural networks that might analyze farms. They might analyze crops. Giving an image of healthy crops, the neural network might tell us that those are healthy crops versus if they are unhealthy crops, it might tell us that there are like some weird bugs in there, like some locusts that we need to kill ASAP, that we need to get rid of. We would want to actually integrate this from our computer. We would want to actually use that either on some cell phone. So we might want to implement the neural network into some iOS. And in that way, someone can take a picture of some crops with their phone, and their phone would give them the answer of whether or not the plants are healthy or not, or on some drone or something like that. Can this be used for human well-being? In what way? Yes, absolutely, it can be used for human well-being. Neural networks are used in pretty much every sector of the economy. Even on your cell phone, whenever you take a picture on your cell phone, if you look closely, you will see like a square that pops up in front of someone's face. That's like the camera that's zooming in onto someone's face. That feature exists in a lot of today's phones. So that is a neural network that is used to look at the image and detect any objects of interest, detect the person's face. So that's one example. We also have Tesla's autopilot. We have many more examples. We have like medical neural networks that can be used to classify diseases. We can use something like classifying whether or not some water is healthy or not given some parameters. So we could analyze whether or not something is safe to drink. If we were to be going over all of the examples, we would be stuck here for decades. I'm not exaggerating. There are so many fields where we can apply neural networks. Out of all of the places that they're applied today, it's probably like 0.1% of the actual areas where we can apply that. So it's a matter of us having the technology to apply it to virtually any field, any industry, virtually any job, with maybe just a few very narrow exceptions. But the economy hasn't really caught up there quite yet. And it's going to take a lot of time to catch up because this technology is advancing very, very quickly. And that's why it will stay in demand for a long, long time. What is the process of teaching a neural network? How many variations, if any, does a neural network need to learn? We are going to be discussing the process. We are going to be discussing a little bit about the inner mechanisms of how a neural network learns very shortly. And right away, I want to say that a lot of people have a lot of questions about that topic. So if you have any questions about that while I'm going to be covering that topic, once again, I invite you to ask any questions. But we're going to be covering that in a few minutes. How many variations, if any, does a neural network need to learn? I'm sorry, I'm not sure I understand. By variations, do you mean different like architectures, prototypes? It doesn't need any. An architecture is just one thing that we are going to be designing in a neural network, and we are going to be training the neural network, and we will be observing if the neural network is learning, if it's given that architecture. If it's not learning, we would try some new architecture. So we would basically try out all of the different architectures until we find one that gives us the best results that we can possibly have. So I think that right now we're going to be discussing how neural networks work. We will be discussing a little bit of the intuition first, and then we'll cover just a little bit of the math, so nothing too difficult. And if anyone has any questions at that point, I will invite you to ask them. So I wholeheartedly invite you to ask any questions that you might have throughout this. One more thing I want to mention, by the way, about math, about needing to know a lot of math and programming in neural networks. Neural networks contain a lot of math, they contain a lot of code, but we won't need to know all of that math off by heart. We won't need to, well, strictly speaking, we won't need to learn any of it. Like middle schoolers take all of our courses and they can create neural networks without any problems. The reason for that is that all of the math and all of the code is already written for us. It's already made for us in the open source libraries that we'll be using in the main course and that almost everyone uses when it comes to any sort of commercial projects. So very, very high-end developers will need that math, like senior developers who are writing their like entire new theories on how neural networks can be used, creating just entirely new concepts, architectures, all of that. They would need to actually know the math, but the vast majority of users, the vast majority of people who actually use this in the workplace don't actually need to know every little step of how all of that math and how all of that code fits together. Once again, it definitely helps. I think that it helps immensely to have at least some basic intuition, but we don't need to know every little step. So the math that is going to be involved in this and the code isn't going to be too complicated. Neural networks. The idea behind neural networks was created way back in the 1950s. A bunch of biologists, actually I'm going to try to make a different picture, decided to draw a representation of how they thought at the time our human brain works, of how, I guess not necessarily a human brain, but how any brain works, whether or not it's a squirrel's brain or a human's brain or some bird's brain or even some insect's brain. We have a bunch of neurons that are connected to other neurons. These neurons contain some information and they're connected to even more neurons. They take in some signal, they do something to that signal, like they might add to that signal, they might subtract to it, or perform some other operation to it, and that would create some output that's going to be fed into another neuron. And that neuron is going to do yet another thing. It's going to do something else to that signal. So that is how biologists thought our brains worked back in the 1950s. We know nowadays that biologists, when they designed their first interpretation, that they were incorrect in a lot of places. But before we found that out, a bunch of mathematicians took that initial model and they decided to make a mathematical representation of it. So they looked at this whole thing, they said, oh, that looks really neat. Let's see if we can make some sort of mathematical representation of it that we can use to actually create something reminiscent of the human brain in a computer. So for a long, long time, computers simply weren't powerful enough. We simply didn't have the processing power. But as time went on, we saw that indeed we can do that. A neural network is just a bunch of neurons that are connected to other neurons. So oftentimes we have what is called a layer. A layer is going to be denoted by these columns. Everything that is in these columns is a layer. And every single neuron in a layer is typically connected to every single other neuron in the previous layer. It takes some data from every single other neuron in the previous layer, and it feeds that data into every single other neuron in the next layer. And that is how we have a neural network. Right now, in our brains, we have neurons. Neurons are in fact made up of brains are in fact made up of neurons. The scientists weren't wrong about that. So A neuron might be responsible for feeling cold. If you are out somewhere on a chilly day, that's the neuron. If you feel cold, that's because the neuron that is responsible for you feeling cold is being activated. It received the appropriate input. It received some inputs from the temperature. It noticed that you are cold and it's activated. It's sending some signal that tells your brain that you are cold. Or if you're feeling tired or hungry or any other thing, if you stepped on a Lego or something like that and ouch, that hurts, that's another neuron being activated. In practice, these are more like clusters of millions of neurons. But for our purpose, what I really want to emphasize is that in a neural network, each neuron is essentially going to classify the truth or the falsehood of some statement. So for example, we might have a neuron that is going to look at the nose, and it's going to check if the nose exists. It's going to check if this looks more like a dog's nose or a cat's nose. We might have another neuron that looks at the tail of the animal. And through the combination of these neurons, we can, usually given an appropriate architecture, given an architecture that is good enough, we can combine all of these neurons to get the final result of whether the whole animal is a cat or a dog. And the neuron isn't just going to give the truth or the falsehood of some statement. It also contains the information as to how true that statement is. So for example, in a very basic example, we might have a neural network that tries to classify whether an animal is a cat or a dog, given 3 parameters. And we're going to be looking at this example later on. Once again, this is purely hypothetical. We might have a neural network that looks at the animal's height, weight, and it looks at the animal's height, weight, and length. And based off the combination of that, it will try to predict whether or not the animal is a cat or a dog. We might have a neuron that is effectively going to ask if the animal has a weight of more than 5 kilograms. If that weight is something like 500 kilograms, like it's way, way more than just 5 kilograms, much, much bigger than 5 kilograms. The output of that neuron will have a very large value. The neuron will output a very strong signal that's going to essentially say that, yes, this neural network is this animal weighs much, much more than 5 kilograms. But if the weight is something like 5.1 kilograms, it's going to give a very weak output. Like it's going to say, yes, that this animal weighs more than 5 kilograms, barely, kind of, not really, barely more than 5 kilograms. So each neuron is going to classify the truth or the falsehood of one condition. Looks like gate logic. Yes, it is very reminiscent of gate logic. So this is where our basic neural network, what is called a dense neural network, comes into play. A dense neural network is basically a fully connected neural network that looks like this. We have neurons over here denoted by these big blue blobs. These neurons contain some value, like a value like 0.1. So in the first layer, we have the input values. These are the values that we feed into the neural network. In our case, it's going to be the weight, the height, and the length of some animal. Then we also have weights. Weights are these lines that connect 2 neurons together. And these also have some number associated to them. So numbers are going to propagate through this entire neural network in some fashion through all of these layers. So these 2 layers that we have right here, they are called hidden layers, these 2 layers. These are the layers between the output layer and the input layer. They will perform some mathematical operations. We will be discussing which mathematical operations they'll perform, and then they'll give 2 neurons. In our case, we have 2 neurons on the output. It really depends on the matter at hand. In our case, we have 2 neurons right here because we are trying to classify cats from dogs. So we will have numbers propagating through this neural network. And then we have this neuron that corresponds to how much the neural network thinks the input corresponds to a cat. And another neuron that is responsible for how much the neural network thinks the output corresponds to a dog, or the input corresponds to a dog. So for example, we might have a final value of 1 for cat and 0 for dog. This would mean that the neural network is very sure that whatever we gave it, whatever information we gave it, that it corresponds to a cat. It is absolutely certain that that's a cat and not a dog. Or we might have a result that looks like this. This would mean that the neural network thinks that there are some features that are reminiscent of cats, so it might be a cat, but it's considerably more sure that whatever the input is, that it corresponds to a dog. And if we had 3 different categories, we would have a third neuron. If we were to, for example, try to classify cats, dogs, and beavers, something like that, then we would have this third neuron that's going to contain the information of how much the neural network thinks that the input corresponds to a beaver, and it might have some other value. And in this case, we would be taking the largest value. So in this case, we have 1 for cat, 3 for dog, and 2 for beaver. That means that the neural network thinks that whatever the input is, it corresponds to a dog much more than to a cat or a beaver. So the neural network is going to then say that the input is that the animal we showed it was a dog. So let's talk a little bit about the actual operations that the neural network performs. We have neurons that contain some values. The input layer contains the initial values that we feed it. So these are numbers that we give the neural network. These are the first numbers. Just for example, they might be something like this. Let's not work with decimal places. Let's just actually work with whole numbers. And then we have these weights that connect 2 neurons together. So these weights also have values, something like 0.5, for example. All of these other neurons. So for example, this neuron, its value would be the weighted sum of all of these neurons. So this neuron would output the value 1 times this weight, which is like 0.5. So we would have 1 times 0.5 plus 3 times, let's say that this weight is 1, plus 3 times 1, and we would have plus 4 times whatever its weight is, and so on. And we would repeat this procedure for every single neuron. And in this manner, these neurons are effectively going to be asking questions. So we have these weights here. A neuron might ask, for example, if the height of the animal is more than twice its length. So in that case, we would have the height here, like this number 4, and we might have a value of 1 for length here. Then this weight would have a value of 0.5 or negative 0.5, and this weight would have a value of 1. So we would perform that addition. Actually, this would probably be positive and this would be negative. So 4 times 0.5 plus 1 times minus 1 equals 1. So that would mean that since that neuron's value is more than 0, that condition was met. Indeed, the animal, its height was more than twice its length. So it's probably a bipedal animal in this case. Or another neuron might ask a different question. Is the weight more than the height times the length, and so on? These are all of the questions that the neurons in this layer might be asking. So the first layer might just be asking even more basic questions, like, does the animal weigh more than 5 kilograms? And if it doesn't weigh more than 5 kilograms, we might not have an output here. The output would be 0 from this neuron. This layer, the neurons in this layer, would be asking more complicated questions, like the combinations of all of the weights, lengths, and heights. The neurons in each successive layer will be asking even more complicated questions. And eventually, the neural network will ask questions that are complicated, that are complex enough to be able to categorize or perform any other function that we want it to. So in our basic example, we only have like 4 neurons per layer. In practice, we are going to have thousands of neurons in every single layer. So we will have thousands of neurons asking all sorts of questions. And we won't just have 1 or 2 layers. We will have dozens of layers. So a neural network, that's how it operates. Now let's discuss how the neural network actually learns. As we've mentioned before, when the neural network is born, it doesn't know anything. When it's born, all of these weights that we have here are going to be just purely random values. So the questions that it's going to be asking are effectively just complete and utter nonsense. It might ask a question like, is the weight at least 1 million times bigger than the height minus the length, or something absolutely weird like that, which is going to be the case for every animal. Every animal, I think, weighs less than 1 million times more than its height measured in centimeters or inches or something like that. And all of these questions are going to be absolute nonsense, and the output is going to be absolute nonsense. We are going to give the neural network a bunch of data to learn from. So this is called the training data set. This is the data set where we would give the neural network examples of some animals' weight, height, and length, and we would then tell the neural network what animal that corresponds to. So the neural network might look at these parameters first, and it might say that this corresponds to a dog. But then it's going to see that it corresponded to a cat. And that's when it's going to say, darn, I was wrong. So it wasn't a dog, it was a cat. And it's going to try to change all of its weights in such a manner that whenever it receives all of these inputs a second time, the answer that it's going to give is going to be closer to the right answer. There is no guarantee that it's going to be the right answer. For example, it might still say that this is a cat the second time around, but it might be a little bit less certain. But we would be going through this whole data set many, many times. And the hope is that eventually the neural network will learn that whenever we have this combination of data, that actually corresponds to a cat and not a dog. If it guesses correctly the first time around, then it doesn't change any of its weights. It got the right answer. It doesn't need to relearn. It doesn't need to change anything. But whenever it predicts something that is wrong, it's going to say that since that answer was wrong, it's going to change all of its weights in such a way that the next time it receives all of that data, it's going to give something closer to the right answer. So we would be performing this procedure on all 20,000 examples. And 20,000 examples is not a large data set, by the way. Depending on the context, if these were images, this would be a medium-sized data set. If we have just 3 parameters, this is a tiny data set. And then we would go over all of these 20,000 examples again and again and again. And whenever we go over all of these 20,000 examples once, that is called an epoch. So one epoch is going over all of this information once. We might have 100 epochs, and that's still going to be for a fairly basic neural network. And finally, we have the test data set. So when we train our neural network, the hope is that it doesn't just memorize all of these combinations and that it doesn't just know that this exact combination corresponds to a cat, but that it knows that it has actually learned some information. So if we were to feed it some data that looks similar, but we were to change the weight slightly here, it would still predict this as a cat rather than a dog. So that's the purpose of the test dataset. The test dataset contains data that isn't present in the training dataset. And the hope is that the neural network can also classify all of this data that it's never seen before. And if it can do that, then we're good. If it can't do that, then something was wrong. There is some overfitting going on. We need to either change the architecture a little bit, or change the data set up a little bit, or try to do something along those lines. So we only really care about how the neural network performs on the test data set, because that is going to give us the knowledge of how the neural network is going to perform in real life. We don't care about the answers that it gives on the training dataset. The purpose of the training dataset is just for the neural network to learn. If you think about practice exams, like teachers, professors really don't care how well you do on your practice exams, right? They won't give you an F because you failed your practice exam. They'll only give you an F if you failed your final exam. So that's what we care about here. So the entire process of training a neural network consists of changing its weights. Every time the neural network predicts an incorrect answer, it goes back and changes all of its weights in such a manner that the next time it sees that data, it predicts something closer to the correct answer. It doesn't actually change any of the neurons or any of the biases, activation functions, and a bunch of other parameters that we have in neural networks. It doesn't do any of that. We give the neural network its architecture. We define the architecture. All the neural network does is set the weights in the appropriate manner. And that is going to be controlled by a certain algorithm that we are going to discuss very shortly. So to recap, a neural network has some architecture that we will define. So we will say that all of these neurons, we have this many neurons and they're connected to each other in this sort of specific fashion. And the neural network, when it trains, it is going to set all of its weights accordingly. We don't actually control any of the weights. We only control the architecture. So when we train neural networks, all of these weights are going to be adjusted. They're going to be adjusted in a way that gives a more correct answer. If the first time around, the neural network effectively asked a question like, for example, this neuron asked a question like, is the weight of the animal at least 10 kilograms? But we have a bunch of dogs or actually, let's say that it asked if the weight is more than 1 kilogram, but virtually all cats and dogs weigh more than 1 kilogram. So that's not a very good question to ask. This weight might change. We also have a bias here. A bias is basically just addition. It's something that performs addition, whereas the weight performs multiplication. These variables would change in a way that the neural network might then ask if the animal weighs more than 2 kilograms, which not all cats weigh more than 2 kilograms. So that might be one distinguishing feature. But maybe some cats still weigh more than 2 kilograms. Maybe we're looking for something like 2.5 kilograms. So if we train the neural network again, these weights will be rearranged in a way that the neural network will essentially be asking if the weight of the animal is at least 2.5 kilograms. And this is where gradient descent comes into play. Gradient descent is the algorithm that controls how we change all of these weights. A lot of people have questions regarding this. So if you're confused at any point, once again, I will be more than happy to answer any questions that you might have. Essentially, when we perform this operation of multiplying and adding numbers, of multiplying and adding all of these parameters to get our final answer, we are then going to see if that answer was correct or incorrect. We are going to have something that is known as the loss value or the error value. So this is a single number that classifies how wrong we were. For example, if the neural network was 51% sure that the correct answer was a cat and 49% sure that it was a dog, but it was actually a dog, That's not as bad as the neural network saying with 100% certainty that the animal is a cat and it turns out it's a dog, which was the 0% prediction. Or if we're predicting a single value, we might say that the temperature tomorrow is going to be 50 degrees. But it turns out that the temperature was 20 degrees. That is a huge error. We were off by a ridiculous amount. That isn't as bad as being off by just 1 or 2 degrees. And the error function is going to basically state how wrong the neural network's prediction was. A large error value corresponds to something just being completely wrong, whereas a small error value corresponds to the neural network being more or less in the right ballpark. So we want to decrease the error value. We want to decrease the error value as much as possible, and that's when we are getting our right answer. We can plot out this error function. Sorry, not error function. Error function is something completely different. We can plot out this loss function. We can make a rough plot of it using all of our different weights and biases as parameters. So just to go into a little bit of math, if we have a function of one parameter, that's going to be just a one-dimensional line, right? If we have a function of 2 parameters, this is going to be drawn in 2 dimensions. All of our biases and all of our weights are going to be different parameters. So effectively, we are going to have millions of dimensions in this graph. Like a million weights in a neural network, that's still a very small neural network. We will have tens, hundreds of millions of dimensions in this graph. So this is a gross oversimplification. This is just really oversimplified of what this graph might look like as a one-dimensional line. But no matter how many dimensions we have, whether we have 1 dimension or a quintillion dimensions, the logic will stay the same. We will know where we are on this function. We won't know what this whole function looks like. We just know where we are. That's on this dot. We have an error value like this, and we know what the gradient at that point is. So we would know that if we zoom into this area very, very closely, we would see a flat line that looks like this, and that is our gradient. We know that if we head in this direction, then we will head down the gradient and our loss value will decrease. So the gradient descent algorithm goes back through the entire neural network. It looks at all of the weights, at all of the parameters, and it changes all of the weights and biases in such a fashion that we are essentially going to take a small step down this error, down this loss function to get a new error value. And after we take one step, we are going to perform the exact same analysis. We have changed all of our weights. The neural network is giving answers that are a little bit more correct, a little bit less random, but our error value is still very large. So that is where we perform this exact same procedure again. We would see that we are located here. We need to go in this direction to head to decrease our error value even further, and we would keep doing that until we reach some local minimum in this function. In theory, we would want to reach this local minimum. In practice, this is where a lot of overfitting tends to happen. So we don't actually want to go here. We would want to go to some reasonably small local minimum, but not to the global minimum. So something like this would be nice. However, there are a few dangerous moments here. When I drew these little hops, I drew them using a very convenient sort of hop size. However, if we were to take very, very small hops, we run the risk of eventually going down somewhere here. This is where our neural network has basically not really learned anything. It's learned very little. But then it's going to perform this exact same procedure. It's going to look at which direction we need to go to decrease our error value. It sees that we're located here. It's going to see a gradient that looks like this, right? And now it decides that we need to go in that direction to decrease the loss. and then we go back where we started. Once again, it does the same thing. It sees a gradient like this, says that we need to go here, and we just keep doing this forever, basically. In practice, this doesn't tend to happen too often. Well, sometimes it happens, but not too often for a few reasons. We can also take very large steps, in which case we would drastically change all of our weights. And we would just take a massive, massive hop all the way onto the other side of this whole line, of this whole graph. And then we would perform the exact same procedure. We would see that we now need to go that way. And then we go back, we hop back again. And once again, we don't really learn anything. It just keeps doing this forever. So in practice, this doesn't tend to happen too often for several reasons. We have what are called optimizers. Optimizers change the size of these hops. So if an optimizer sees that if we're getting stuck in some local minimum, it's going to try to increase the size of these hops in order for us to navigate over this curve and keep making progress down until our better local minimum. And if it sees that we are taking hops that are too massive, it's going to reduce them until, once again, we get some proper results. So the math that is involved here, once again, is quite complicated, but all of that is built into our frameworks, into our open source libraries that we will be using, so we won't need to know all of that in great detail. But if you do want to know that, all of that, for any reason, we have a whole course that talks just about all of the math. So the other reason that this doesn't tend to happen is that we don't really have one-dimensional graphs here. We have many dimensions. Like right now, I'm trying to draw a second dimension, but in practice, we have millions of dimensions. So that is how gradient descent works. So to recap, it changes all of the weights in such a fashion that the answers given by the neural network will be less wrong, until eventually they usually won't be exactly spot on in practice, but the error will be so small that we will basically say that the neural network has learned how to do all of this, how to perform its function to an exemplary degree, and we will be happy with that. And with that, let's go on to a live demonstration. So this is Google Colaboratory. This is where we will be coding in our main courses. This is where we are going to be writing all of our code. So this environment looks like this. Google Colaboratory is very convenient for a few purposes. Any code that we write here is going to be executed online. It's going to be run on Google servers. So even if you have just a very old laptop that you want to use for the purpose of this course, that will do just fine because all of the number crunching is going to be done by Google servers. And the second advantage is that Google Colaboratory allocates a GPU that we can use for the purpose of making neural networks. Google Colaboratory's GPU, it's actually quite high-end as well. Like buying something like that on the market would cost something like $1,000. So Google lets us use that GPU for like 12 hours a day, which is more than enough for our purposes. We can write any of the code here, and all of the number crunching will be done by Google. Our university has created some libraries that contain all of these neural networks. So all of this code is pre-made. When you're writing all of this code yourself, it won't be quite this easy, but it won't be very complicated either. It's still going to be relatively simple. So right now, we will be waiting while this neural network loads up. This first example, we are going to look at how a neural network can classify between cats and dogs. So once again, just a very simple example, very simple neural network. Let's initialize our model. So this step takes quite a bit of time. It's like downloading like 25,000 examples, 25,000 different images. So if you have any questions in the meantime, or you want to discuss anything, So while it's doing that, we are just going to wait a little bit, and then we will train the neural network. So once again, this is a very simple neural network, and that's why it's going to train in like a few minutes. Or I think it's like not even a minute. So there we go, it's downloaded some examples. These are what our pictures look like. We have different cats and different dogs, and the neural network has to classify which of these are cats and which of these are dogs. So when we train the model, we have two parameters that we are going to be looking out for. We have the accuracy that the neural network has on the training set. So this is data that the neural network has already seen, and this accuracy tends to go to 100% quite quickly. It tends to go to 100%, but that is usually because the neural network has some, you could say, muscle memory. It has already remembered that data in some way. The only parameter that we really care about, excuse me, the only parameter that we really care about is the accuracy on the test set. So as we train the neural network more and more, we see that both of these parameters are increasing. That's good. Sometimes we have a case where we train the neural network and the training accuracy is increasing, but the accuracy on the test set is decreasing consistently. And that is very bad. That means that we have some really bad overfitting going on. But we don't have that going on here. So that means we're good. And if we were to keep training this neural network, it could maybe reach 93, 94%. Looks like Python. Yes, thank you for reminding me. Yes, we are going to use Python to code all of our neural networks. They can be loaded, they can be coded using other programming languages, but most people use Python because Python has the best libraries. It has the most support for all of these libraries. I think like other languages like JavaScript also have support for TensorFlow. I don't know about Keras. So Keras and TensorFlow are the names of our two libraries. They've actually been integrated into one library. So that is what we are going to be using during our courses. You can make them in any other programming language, but the vast majority of just commercial projects in general are done using Python. So yes, this is Python. Thank you for reminding me to tell that, by the way. So if we plot our accuracy versus the epoch. So remember, the epoch is how long it takes, or rather it's the epoch is when we go over all of the data in our training set once. So if we plot out the accuracy over the epoch, we can see the training accuracy plotted in this blue line that looks like this. So it tends to 100% quite quickly. And the accuracy on the test set really lags behind. That happens a lot. That's not bad. That's not necessarily bad. Like, it is bad that we're not getting better accuracies, but what we're really concerned about is if this accuracy was to go like this. That would be really bad. And we want to avoid something like that. If we were to get something like this, that means we have overfitting going on, like the overfitting of the really bad sort that we want to avoid. So if we were to make an intuitive plot of this, if we were to show some images, show this in image data, we can see that in the first epoch, the neural network just isn't sure which animal is which. It just clumps all of it into one single bin. But as we train it for more and more, we can see that the neural network learns to distinguish all of these animals. It knows, it has learned to, it's associated some difference between these animals. And the more we train it, the more difference it sees between all of these animals. So that is very good. We have accuracies of like 93, 94% here, but out of all of the examples that we have here, all of them are pretty much classified correctly. So once again, that is good. In our next problem, in our next example, we have a regression problem. Regression is when we want to classify one specific number. So if we have cats or dogs, we want to classify a category, like is the image a cat or a dog? Regression is when we want to classify one specific value, like how much something is going to cost, what the stock market is going to look like, what the opening stock market prices are going to be 5 days from now, what a company's income might be a month from now, or we might predict several parameters. We might predict something like the weather, or rather the temperature, the humidity, wind velocity, humidity, CO2, and a bunch of other numbers like that, how cloudy it's going to be. But all of these, they are not going to be separated into categories. They are going to be specific values. So like 45 degrees or 46 degrees. So in our regression problem, in our example problem, we are predicting the prices of cars. We took some data from a data set. I forgot to run this line of code. And this data looks like this. We have some car manufacturer like Volkswagen, the model, the year it was produced in, the mileage, fuel, like if it's a gas or a diesel car, and how much it costs. So this is what we want to ideally predict. This is real data that was taken from some website, that was parsed from some website. So we want to create a neural network that is going to predict all of this data, and given a new combination of parameters, it's going to tell us how much we can sell that car for example. So we have some other parameters here like body and KPP. Even though I've seen these parameters quite a few times, I still don't know what they are. And the great thing is that I really don't need to know what they are, because the neural network is going to find that out on its own, and it's going to find out how much it affects the final price on its own. So let's train the model. Once again, it's a fairly simple model, so it should train pretty quickly, especially since we're using a GPU. At the start, the loss, so the loss in this case, we don't have accuracy, we just have a loss, which is how off we were. And we could define the loss as being off by the exact number of dollars. We can define this by being the number of dollars squared, or we can define any loss function that we want. In our case, we decided to use the linear data. So our loss is exactly how much we were off by. In the first epoch, the neural network doesn't know what it's doing. So it's off by an average of $15,000. If a car costs $15,000 and the neural network predicts that that car is going to cost $0, it's going to be off by $15,000. So this is really abysmal. But then, as we train this neural network for more and more epochs, we start getting better and better data. So after 30 epochs, we're only off by $3,000. And after 50 epochs, we are off by like $2,800. So this number keeps going down and down, and it looks like it's reaching some sort of asymptote. So that's where it really isn't going to learn anymore. In fact, if we were to keep training this, we run the risk of the loss function looking like this, which would be very bad. So to get even better results, we would either need to change the architecture of the neural network and train it again, or we would need to do something with our data set, since a lot of our results actually depend on our data set. So some other notes about this. The difference between the training loss and the test loss really isn't big. So that is also very good. The neural network isn't overfitting. We see that at first it wasn't overfitting at all, but eventually it started to overfit a little bit. That's not very good, but that's not too terrible either. Once again, the only thing we really care about is this orange line, this test loss. If the orange line is small and the train loss is even smaller, that's just as well as if the test loss is small and the training loss isn't any smaller. We only really care about the loss on the test set. And if we were to visualize this process using a scatter plot, on the first epoch, it would be off by quite a bit. Unfortunately, we don't get to see the first epoch here. But as we keep training this for more and more epochs, these blue dots and these red dots start to converge, which is really, really awesome. So once again, that means our neural network is learning, and the data that it's predicting is getting closer and closer to the actual data. And for our final example, we are going to look at image segmentation. So image segmentation is when we can either have a picture and we can draw lines, like we can see that, for example, maybe this corner contains some person, maybe this spot contains a car, and we would highlight those in different colored boxes. Each category of objects would be highlighted in different boxes. But in our case, we are going to have masks. That's when we are going to look at the picture pixel by pixel, which is an even more complicated process. Okay, unfortunately, we are running out of time, so I'm going to try to go through this a little bit quicker. Right now, we're downloading some images, and our images, they will just be airplanes that we will want to find out where the airplane is versus where everything else is. So our airplanes look like this. That's this top row. And our goal is to get images that look like this second row. So where the plane is highlighted in red, every single part of the plane is highlighted in red, and every other detail is just blanked out. That is what we want. And we can try out a few different architectures in this manner. We can try out, for example, this predefined architecture, the U-Net architecture. We can see that it gives us results that are reasonably good. So the accuracy on the training set, which we don't care about too much, so it tends to go to 100%, we really only care about this. So the accuracy on the test set started out very bad, like 15%, that's absolutely terrible. But by the end, it's reached like 98, and then it jumped down to 96%. So that's unfortunate, but that happens. Oftentimes, we get examples of the accuracy of the neural network training, but then it decreases, it falls in accuracy. That's what we have here, but then it jumps back up. We are fine with that. That's not too bad. We only really start to be worried when we see the accuracy on the test set consistently decreasing. That's it. That is when it's very bad. So in the first epoch, we got results that are very bad. Like everything was predicted as part of the airplane, and we just got this big red blob. And then we start to see something that is vaguely reminiscent of an airplane. So third epoch, we get something that's better, and for fourth epoch, we get something that is worse. Happens. Sometimes the neural network trains, and after it has finished training, it is worse than before it started training on that epoch. But then it jumps to even higher accuracies. So that wasn't too terrible. Now we are starting to see something that is more and more reminiscent of an airplane until we just get perfect results. And then when we apply this mask on the airplane, we get the exact result. Then if we were to try to perform this exact same procedure with a simpler architecture, this linear architecture, our results aren't as good. We really only peaked out at about 82% accuracy. And notice that it's the same for the training set. So this gives us some information that the architecture really just isn't powerful enough. And the results that it gives, interestingly enough, it does a very good job at outlining the contours, but that's not what we want. So it didn't give us very good results. And then we would try out another architecture, this PSP architecture. And here we see some serious overfitting. We see the accuracy consistently decreasing. It's not decreasing by too much, but it is decreasing. And it's much lower than the accuracy on the training set. And if we were to visualize this, who builds the architecture? We build the architecture. These are just some predefined architectures that we have lying around in our library. In practice, you would be writing some code like model equals sequential, and then you would be adding more and more layers. Like this is one way you could do it, model.add, and then you would specify the layer, how many neurons you want, what activation function you want, and stuff like that. And you would make a bunch of these layers, and then you would have some output. But this is just for demonstration purposes. We have some neural networks that we just built ahead of time lying around. So this PSP architecture, it wasn't as good. It didn't give us the best results. It gave us some decent results, better than the linear architecture. But we see that both of these architectures really don't perform as good as the U-Net architecture. So that's when we would want to take a look at the U-Net architecture. And we might want to make some improvements on top of that. We might decide that 96.5% isn't good enough. We want 98 or 99%. So that's when we would try to tweak this architecture just a little bit to give us even better results. Okay, with that said, we are going to go back to our presentation. So we have a course. We have our main course that deals with data science and neural networks, where we start off with the basics and we go over tons and tons of examples. We go over 26 different subjects like text classification, classifying images, regression, and then we head on to autoencoders, deep neural networks, and a bunch of other things. So we start off with the basics, and towards the end, we cover a lot of in-depth material, a lot of higher end material. So at the end of our courses, you will be able to become a junior AI developer in whichever company you want. In fact, as a part of our contract in the course, we actually guarantee job placement. We have our own domain, we have our own website where we network with all sorts of big companies that hire our graduates, people who have graduated from our courses. We have people who will advise you on how to build your resume, what to include. You might include something like your final thesis project or any other experience that you have programming of something, if you have any. And we guarantee job placement at the end of that. In the United States, AI developers usually make between $45,000 and $85,000 a year for entry-level developers. This is like your first job in the field. If you've never programmed before, if you've never had any experience developing AI, these are the wages that you can typically expect. So 45,000 is somewhere in like the Rust Belt, Middle America, some small towns. 85,000 is something like New York, California. So these are, a lot of this depends on geography. And these are the starting wages. The wages for like really skilled developers that have a lot of experience, they can easily go up to 300,000. These are like only the really, really good professionals make that much money. People who have like 10 years of experience. But some people do reach that point. Like 45, 85,000 is really only the starter wage. Is it work from home? I think that in light of current circumstances, coronavirus, a lot of people are going to be working from home. Before, whenever we, like a year ago, whenever we had these same webinars, whenever we talked to our previous students, we said that it's only a matter of time. Actually, I'm going to say that as well. We guarantee job placement. It's only a matter of time. We guarantee job placement for everyone. It's only a matter of time until you find your job. So on the highest, so on average, it takes like a few months. On the highest end, it might take, I don't think it's going to take over a year, but that's like the absolute worst case scenario. It depends on your criteria a lot. Before, we would say that if you want to work from home and if you want to work in some specific industry, that might take a little bit longer. But right now, I think everyone's working from home, so I don't think that's going to be a problem at all. So job placement is, once again, I want to emphasize, absolutely guaranteed. We have that written out explicitly in our contract, in the contract that you will be signing when you take our courses. So we have two streams. We have the light stream and the pro stream. The light stream is geared towards people who have never programmed before, who don't know what programming languages are, stuff like that. So people who come to us from all sorts of backgrounds, fresh out of high school, fresh out of college, university, people who are like doctors, bankers, mechanics, any sort of job really, that doesn't have a lot to do with programming. But for people who have some experience programming, we have a different course, we have a different stream that is called the pro stream. So the pro stream goes over the exact same material. It just sort of starts later on. So in our light courses, we start with the very basics. We start by teaching you the very basics of programming. We start by going over the very basics of some of the things that you need, like some of the mathematical concepts that we need for neural networks, or that we would benefit from just a little bit. We would touch upon that. We would look at all of the libraries that we're going to be using, and we have 13 lectures just for that, just to prepare you for the meat of the course where we are working with neural networks. People who have programmed before jump straight into neural networks. Even if you haven't programmed with neural networks, even if you've been a game developer or a web designer, something like that. So for people like that, these people, they typically have the programmer's mindset. So we've decided that, and we have some practice that backs this up, it's much better to just start with the meat of the course and just keep going from there. So our pro stream consists of 26 courses that you'll finish in 6 months instead of in 9 months. And oftentimes you will be able to become a middle AI developer, especially if you have some proper, like some job experience in programming in any other field before. You can become a middle AI developer straight off the bat. And the wages for that are something like between 60 to 120, like 65 to $120,000. Once again, depends on the geography, depends on the company you're working for, and so on. So AI development is a really new field compared to all of the other fields, like game design, web design, to data science. So compared to programmers working in all of those fields, AI developers usually make a little bit more money. And right now they are immensely in demand. And if you already have some background in some other area, some other industry, then if you master both trades, that is just going to be super amazing. Like you could actually apply artificial intelligence to create enemies in some video game instead of having them be controlled by some dumb algorithm. So that is one field that you can apply them. You can apply them to generate some content for video games. So there's a lot of very interesting applications. A lot of people who also come to us, they come to us on behalf of some other companies. So on behalf of some other company sends us their developer. They ask us to sort of teach that developer how to make neural networks, everything regarding neural networks. And at the same time, they would want some specific neural network to be made for some specific area related to that business or whatever the company needs. So in that case, we have a team of advisors that can start advising you from day one. For those people, we have advisors that can start from day one telling you how to create your data set, what data to look for, how to create your neural network. So by the end of the course, you will have both learned how to build neural networks, and you will have created the actual neural network that your company needs. One more thing I want to mention. Whenever developers are creating neural networks in general. Very rarely will you get scenarios like a company contacting you, asking you to build some neural network, and then just you will like make the neural network and they'll say, oh, cool, neat product. Okay, thanks, bye, here's your money, goodbye. Very rarely is that going to happen. Usually they will want to keep those developers around. They will want to either update the neural network to fit any more current circumstances, or they would want to keep improving that neural network. So you could land yourself a permanent position by building a neural network for some company pretty often, like a permanent position to maintain that neural network. I have very limited coding experience. Would jumping in the middle developer course be too much, or is it possible? You could try, and if you find that it's overwhelming, you could switch to the light course. The first course in the light stream is just the very, very basics of Python. So if you have any coding experience at all, especially if it's Python experience, you wouldn't be really missing anything. Like you could try out the first lesson in the pro stream, and if that doesn't work out, you could switch. That's absolutely free. But in general, we recommend people who have at least 1 year of development experience to take the pro stream. Otherwise, I would take the light stream. So in your case, I would take the light stream, and I'm going to explain a little bit more why. So our courses, they start on the 26th of September. That deadline is approaching fast. It's a little bit over a month from now. So we have the pro stream that lasts for 6 months. It consists of 26 different lectures. We normally recommend you to spend 1 week on each lecture. And then there is homework at the end of each lecture. And same thing for the light stream, except we have 13 bonus lessons that are geared more towards light users. So how to program and all of that sort of stuff. So each lecture comes out about once per week. They are recorded because we have found that recorded lectures are much better. They are like people like recordings much better than live lectures. And so we have 1 lecture per week. We have homework at the end of each lecture. And at the end of the course, we also have a final thesis project that you will be working on. Right away, I want to say that no one ever fails the thesis project because we have a whole team of developers that can help you with any questions regarding your thesis project, regarding any little details that you might have, any little questions. And once again, I want to emphasize that we guarantee job placement. That is going to be written out in our contract. So far, we have never had any graduate from any of our courses that hasn't been able to find a job within a reasonable amount of time. So we have a whole team of TAs that can help you with any homework related question that you might have. You can contact us in whichever fashion is going to be more convenient for you. You can text us, you can email us, you can book a video chat with us, and we will be more than happy to help you with any course-related topics. So we check homeworks, we provide feedback on what you could have done better or if you made any mistakes, and then we also always give the opportunity to fix that homework, and then we check that once again. I learned how to program on Turbo Pascal 25 years ago and never really used it. Did medicine and teaching for a decade, no programming. I have been trying to teach myself Python via a basic book, but not doing the homework. Seems to make sense, but not memorizing or using it. ProStream okay, or I should do Lightstream? I would recommend the Lightstream, but you could try jumping into the ProStream. If it becomes too overwhelming for any reason, you could hop back into the Lightstream. Personally, I would recommend the Lightstream because we're going to teach you a little bit about how to program in Python. Turbo Pascal, wow. Programming on Pascal, excuse me. programming on Pascal is much, much more complicated than programming in Python. Modern programming languages are very simple in comparison. So we also have a course coming out right now where we talk about just programming in Python, just pure Python, much more in depth. So maybe you might also be interested in that. But yeah, in general, I would recommend the Lightstream. They have the exact same price, so you're not going to be, you just basically get more content, right? But it's up to you. The theory is that people who have the programmer's mindset would jump into the pro stream and they would sort of catch up with any syntax related issues in Python fairly quickly because they've programmed in some other languages. But I don't know if we have time to do that because, well, I'm going to mention one more thing. So right now, I want to mention that all learning is going to happen remotely. So everything is going to happen remote. The final oral exam, everything is going to happen remotely. All of the homeworks, checking all of the homeworks, any consultations that you might need. And then we also issue a degree at the end of that. So we issue like an actual certificate. And we can either mail that to you or send it to you by courier, whichever is more convenient to you. So in terms of pricing, for both courses, they cost $3,490. That comes with 39 or 26 different lessons for whichever course you've taken, either a Lightstream or the ProStream. That comes with 24/7 TA assistance, and I'm not exaggerating. We have people working around the clock 24/7 whenever is more convenient for you. We usually take like 10-15 minutes to respond. If we're super busy, we might take a little bit longer, but if we're super busy like consistently, then we'll just hire more people. So usually we respond like within 10-15 minutes, 24/7 for the entire duration of the course. Someone raised their hand. If you could please just ask the question because I don't know what to do with raised hands. I'm not too familiar with the Zoom's interface. So that also comes with guaranteed job placement. Once again, I want to emphasize that. So far we have unpaid internships. We are looking towards making them paid internships. By the time you complete the course, we might have paid internships, but no promises on that. But even an unpaid internship, that's like 10 hours a week, and you can include the results of that in your resume. And that also comes with the certificate. So you get a nice looking certificate that we can either mail to your home address or we can send a courier to deliver it to you physically, to hand it to you. And everything else is also going to happen remotely. So some companies actually look at that certificate, and on our domain, they actually look for graduates from our courses. I have a Bachelor of Science already. Do you have a degree title for Master's in Science of this wonderful program? A degree title for Master's in Science. I'm sorry, I'm a little bit confused because a master's degree is not the same as a bachelor's degree. In any case, I'm not sure. I would recommend asking our sales managers regarding that. So one moment, please. I'm just going to drop the contacts of our sales departments. I think they will be able to answer that question better than I will. Sorry about that. I don't actually know. So any organizational questions, I think the sales department will be able to answer that better than I will be able to, but if you want to ask that, I will try to answer that anyway. Okay, we're really running out of time. So for payments that happen before the 28th of August, we have 2 gift courses. So regarding the question whether or not you want to take the ProStream or the Lightstream, as the gift course, we have this course, Basics of Python course. And we are going to be handing it out to the pro users. So it contains the first 7 lectures from the Lightstream. covers all of the frameworks that you need to know before heading into neural networks. Right now, we only have a month left before the start of the course, but if you want to try, you can still try to complete that course on your own, and that's going to give you all the knowledge that you will need. So that's going to cover all of the bases, any information that people learn from the light course anyway. Or if you want to take the light course, you can still take this course. But we would, since you'd be covering that, all of that material in the main course anyway, we would recommend to take this course. This is the course that we're making right now, Introduction to Programming. So we're just covering the very basics, like what programming languages exist out there, where we can apply programming, all of that sort of stuff. And we also have this eTotal course, the Introduction to AI course. We basically go over this is a very laid back, chill course. So like no homework involved, only lectures where we go over all of the materials, like theory related stuff, mostly like how people create data sets, what the whole process of that looks like. We talk a lot more in depth. We go into a lot more depth about what we covered in today's lecture. 7 courses. And for payments that happen before the 28th of August, you get 2 free gift courses. And that concludes today's presentation. Everyone, thank you so much for watching. Thank you so much for listening. And if you have any questions right now, I will be more than happy to answer them. Any questions, their organization, like logistics related questions, no guarantee that I'll be able to answer them, but I will try. The internship is done remotely, yes. Everything is 100% remote, which is a very good thing because of coronavirus. So I don't think finding a remote job will be of any problems given today's circumstances. Thank you. I'm glad that you enjoyed the presentation. So if anyone has any questions, I'm just going to, so one thing I'm going to do is I'm going to drop our university's contacts. If you have any questions regarding how any materials in the course, you can contact them by email, by phone number, or you can go on the website. There is a little chat box that pops up on the website where you can ask any questions right away. So if anyone has any questions, my Zoom's interface is glitching out. So yeah, if anyone has any questions, I will be happy to answer them. So that concludes today's presentation. Everyone, once again, thank you so much for watching. And I hope to see everyone in our courses. Take care, guys. Okay, we have a few more questions. Okay, so questions for the sales department. Okay. Have a wonderful rest of the day. Raphael, thank you. I'm glad that you enjoyed it. Have a wonderful rest of the day, night, evening, whatever time of day it is, wherever you are. Take care, you guys. My Zoom's interface is glitching out again.